That's Mount Fuji.
Oh, Mount Fuji, which I have seen actually from
Yes.
a train going between Kyoto and Tokyo.
This is this is from Ashinoko, which is a crater lake in the Hakone caldera.
So Joanna, Scott with you? He's gone invisible. Is he invisible man today?
Well, he's upstairs. We're trying to get onto the live stream, and we seem to have troubles getting onto the live stream. So we're sort of procrastinating. Well, no, we are procrastinating. In fact, we're not sort of. We're just.
The computers are being naughty and complex.
They are, and we're running into some internet problems that it's relatively slow. And so I've been working on that this morning, going, what's wrong? It's not working. And I have all the skill of sitting back there and going, yes, well done. Carry on.
This morning, something happened to me. It not happened before. I was on the computer, and suddenly the screen went completely black, and nothing I could do would do it, would it? So I thought, oh my goodness, what's happening? So anyway, I closed the lid, left it plugged in, came back an hour later, and it was okay. But
all right, we're live.
We have a Scott.
we're live. Okay.
Yep, we're live. Sorry for the late start. Those of you who are joining us online had a couple of little technical glitches,
We glitched.
but everything should be perfectly fine. Fine.
Fine.
Oh, all righty. So welcome to Sidewalk Science, a production made possible by the local Prairie State Humanist group. You can find us on Meetup, Prairie State Humanists. We have several science and philosophy discussions, book clubs and whatnot. And then also the American Humanist Association. And we'll have some exciting news about our collaboration with the AHA here in a couple of weeks. So today on Sidewalk Science, we're going to follow our regular format. We're going to talk a couple minutes about some science news issues.
Stuff.
Science. And then Ivan will talk to us about one of the simplest topics.
Oh, yeah, it's trivial.
Trivial little topic, wave particle duality.
Mhm.
And
We
then,
lost Mike.
he may be, well, it's probably something on his end.
Maybe.
So without further ado, let's talk about some science news. Joanne, you had a story that you were intrigued by.
Yeah, just yesterday, there was this news bit which I was reading that they were exploring in a cave down in southern Mexico, human habitation and all of that kind of stuff. And they were looking around and they were checking the bones and stuff and doing all the things that archaeologists do, and came up to the conclusion that humans had been in southern Mexico 30,000 years ago. So the whole idea of those people arriving on this continent 12,000 years ago, it's been weak, it's been falling apart slowly but surely. We pushed it back to like 18,000 years, but now 30,000 years ago. And that, of course, was the time of the great ice everywhere. We had lots of ice on this end of the planet. And so the only way they could have gotten there was by boat. And so it brings up an entirely very interesting series of questions about how did they get from Beringia down the coast with all the ice and everything else? How did they end up in southern Mexico? But human beings were in southern Mexico 30,000 years ago. And no one knows what's going on. So this will be a huge area of exploration over the coming years in anthropology and that whole area.
So Joanna, I missed the beginning of that, but I was just reading an article in latest Scientific American about migration from Asia to America coming in more than one wave with different
Multiple waves.
Right. And they're doing amazing genetic tests. They find a baby tooth, and they got the DNA from that baby tooth, and they're able to trace these lineages of migrations. Very interesting. Yeah.
Oh, yes. And the whole idea of Beringia is relatively new. No one really had even thought about the idea that somewhere in the northeastern part of Russia, which is supposed to be cold and uninhabitable, there was a civilization there for 40,000, 50,000 years. And that actually generated a complete genetic group of people, which are different from everyone else on the planet.
Is that where the native peoples of
And
the
this is where
Americans?
the American
Yeah.
peoples came from in multiple ways. We know there's at least 3, possibly 4 waves. And this is 16,000 years before that. So suddenly we're going, wait a minute, what's going on? So once again, isn't science wonderful? As we learn more and more, we go, oh my, we don't know what we think we know. Well, we know what we know, but now there's new stuff too. So how do we integrate it all into a whole? And it's just fascinating.
Yeah, so being able to analyze the genome from a baby tooth, and I
Yes.
would say that this was a boy and it was
Yeah.
maybe 10 years old, stuff like that. Amazing.
Yeah, the
Yeah.
American Indian, all of them. When we take any tribe from anywhere from extreme South America all the way up through the Aleutians, they have a unique genetic heritage, which is different from everybody else on the planet. And you could say, are you of this heritage? And one genetic test goes, yep, you are, or nope, you're not.
That's amazing.
Have they linked that to the Australian Aborigines who've been in Australia by themselves for a long time?
No, completely separate group. And I don't know about the genetics of the Aboriginal people of Australia. I would assume that it is also unique, but I don't know that.
Well, I thought they came from Southeast Asia, but then it broke away a long time ago.
Yeah, and it's
Anyway.
separate than the Polynesian peoples of the Pacific Islands.
And it appears, at least at first glance, that this group of people originally came from Africa, and then took that long journey somehow all the way to Indonesia and then to Australia. I mean, what a trek that had been. And there was a lot of people to do it. Otherwise, the genetics would have fallen apart. So we just wandered all over the planet.
We've got our dog here
Yes.
grumping at us. So
So I'm going to pat the dog.
yeah, so he's saying hi to everybody.
He's lying down on my foot now, so I have a nice warm foot.
So some additional science news I was really intrigued by. I've seen, maybe this research has been put together piecemeal over the past couple of years, but I've seen some recent chatter on the science news sites about neutron stars.
Yes.
And the nicer probe, which is better than the others, I guess.
Yeah, well, it's nice.
Yeah.
Well,
The,
we called the original proposal that lost nice.
So this
And
is
then we reproposed the instrument and called it nicer, and it won.
yeah, after making some, did you make changes between nice?
We
and-
made a few. It was pretty much the same thing.
Yeah. So the nicer, is it a gamma ray telescope that
It's
lives
an
on
X-ray telescope.
X-ray telescope? Thank you. And
It's
it
a
lives on,
soft X-ray telescope. We
And it
we
lives-
look at X-rays that are actually so soft you wouldn't use them, for example, to look inside a human body because
Oh.
because skin will stop them.
oh wow.
But they're considered X-rays and not ultraviolet. We go pretty far down, close to the ultraviolet.
And so
Can you
that
explain
the
how you
atmosphere
focus
would break.
X-rays? How do you focus them with bent crystals or something? How do you focus X-rays?
You focus X-rays with grazing incidence optics. You can reflect X-rays off high atomic number metal. We use gold. If the angle of incidence is very small, and so our telescopes consist of 120 concentric, very thin parabolic foils with gold plating on them. And all those parabolas focus down on one silicon detector. And then that's what one telescope is. And then we have 56 of those telescopes on NICER.
wow.
So why was soft X-rays chosen? Is that for the better optics, or is there some?
It was chosen well, partly that the optics don't work at hard X-rays. There's a different, you can make a hard X-ray optics differently, and they do kind of work, but they don't work as well. But the big reason is because we're looking at neutron stars, and in particular, to do the work that Scott's talking about, we are looking at the thermal emission from the surfaces of neutron stars. And that's where the that's the band where the thermal emission is.
Yeah, so the neutron stars are the cooling off cores of stars that started out much heavier than the sun. And they have masses somewhere between, if I remember correctly, like 1.5, 1.6 solar masses up to like 2.3, something like that. So the burnt out cinders remaining from larger stars, the vast majority of the material in those larger stars has been blown away in a supernova. But anyway, there's been a lot of scientific curiosity about the matter, the material that constitutes a neutron star. And one of the hypotheses that has been popular for a few decades is that the very center of a neutron star could be so dense that you essentially have quark matter rather than just neutrons. And you have neutrons because the electrons and protons in the cryogenitor atoms are sort of squished together. I'm simplifying a bit, but they're squished together to make neutrons. So you end up with a ball of mostly neutrons. But there was speculation that in the center regions, it was compressed even further and became kind of a quark plasma or a quark soup.
Quark gluon plasma is the term. But
Thank you.
the term that I invented for that was quagma.
Yes.
Quark gluon plasma. And it's in the dictionary, but it doesn't get used much because people think it's too much like quagmire, which is a horrible, nasty thing you don't want to be associated with.
Well, I assume that you wouldn't want to be associated with the center of a neutron star either. It'd probably be a bit.
Okay. So anyway, because the big thing is the Large Hadron Collider, when we collide lead nuclei together and at great speed and compress the matter, are we making quark gluon plasma? And the consensus is that we seem to be doing that because it's too dense for protons and neutrons to exist. But then the big debate is whether it's what sort of phase transition is going on there. You know, is it type 1 phase transition or type 2? But and of course it doesn't last any time because it immediately blows itself apart.
Right.
But yeah.
So a couple of pieces of news about the hypothetical quark gluon plasma. One is that the very earliest few slivers of a microsecond of the Big Bang saw the universe filled with a quark gluon plasma that is now thought to have had the consistency much like a liquid, incompressible fluid. That was interesting. And then there was some experiments to see whether the radius of a neutron star and the density of a neutron star gave us clues that maybe there was something even denser than neutron material in the inner reaches of a neutron star. And as I understand it, the recent studies show that that does not seem to be happening. That
what we do is that there are hot spots on the surfaces of these neutron stars. They're heated by ordinary plasma impacting along magnetic field lines. It's like aurora on the Earth, but it goes down to the surface, the opaque surface of the star. And so we have these hot spots on the surface. Now the gravity is so strong that light rays are bent by the gravity. And so as the neutron star rotates, we actually see these hot spots move around to the backside of the neutron star, and when we keep on seeing them. And by looking at how fast they're moving away from us or toward us, Doppler shift, and that's where the real soft X-rays come in, because what we need to do is we need to look at the apparent temperature of these things, because they look hot when they're coming toward us and they look cold when they're moving away. We can then deduce just how much bending there is in the light rays. And from that, we can deduce the surface gravity of the neutron star. And that tells, and if we have some measure of the radius, I'm sorry, if we have some measure of the mass, which we do from other data, we then can measure the radius. And the big surprise for this most recent result is that the radius is large. It's at the kind of the edge of where the theorists thought the theory would allow it to be, which means that neutron stars are stiffer than most of the models.
And probably don't have it.
So we can never actually image a neutron star, right? It's always just a point-like object in any telescope. But you think
That's right.
By observing variations in the X-ray emission, you can see about the rotation of it.
Yes.
Yeah.
Well, first of all, it's easy to measure the rotation because I just measure the period. It goes around and it pulses, and it's great. Now what you start doing is you start looking at the profiles of those pulses, and you look at how the temperature, the apparent temperature, changes as the pulse moves around in phase. And it turns out that it's like it's very much like computer-assisted tomography, a CAT scan, where you can deduce what's going on. In a CAT scan, what they do is they rotate the X-ray detectors around your body, and then looking at how things change as they rotate them, they can figure out an image of what's going on. Well, we can take an image of the surface of a neutron star using this technique. And in addition, we can observe how that image is distorted by the gravity and figure out what the surface gravity is.
Cool. So, I mean, back of the envelope, so an atomic nucleus is 10 to the minus 5 times the size of an atom, right? So that means the density of the nucleus is 10 to the 15 times the density of normal matter, right? Yep. So normal matter, like water, is 1 gram per cubic centimeter. Neutron star material is 10 to the 15 grams per cubic centimeter, which is 1,000 trillion times grams. So, and that's back in the envelope. Now, are you saying, John, that actually we think that the density of a neutron star is not as big as the density of a nucleus?
No, I'm saying that we think that the density of a neutron star is not a lot greater than the density of a nucleus.
Okay, all right.
Okay,
So
the thing is that the softer equations of state suggested that the compression in the center would make the density higher than a nucleus. That's not what we're seeing. We're seeing that the material that a neutron star is made of is not very compressible. Its
So
nuclear density, it's a bit higher than nuclear density, but not much.
Okay, so if the center is indeed a quark-gluon plasma, that is no more compressible than nuclei are, right?
I'm an experimenter. The theorists now get to argue over what this means. What I know is what the theorists have predicted, and what we found is on the edge of it is consistent with their stiffest predictions. Now the theorists get to argue about what it means, and that's their job.
So speaking of theorists,
okay, you're passing the buck to theorists.
I am passing the buck. I don't know how to do that calculation. I know how to make silicon detect X-rays.
Are you saying you could measure the radius of a neutron star?
That's what we did.
Okay.
Well, or we measured the surface gravity, which, if you know the mass, is the same thing.
Oh, the masses are different.
Well, but I'm saying that if you know the mass and the surface gravity, you know the radius.
Okay. All right. Okay. Yeah.
so speaking of theorists, I think we need to move on to our main topic for today.
Actually, I'd like to interject first. I have one bit of science news of more user-friendly variety. There's going to be a solar eclipse on Thursday. Only if you live way up north in Canada or Greenland or places like that. But where I live in Bedford, Massachusetts, if you're willing to get up at sunrise on Thursday, you will see a rising partially eclipsed sun, which is pretty fun if you're willing to get up at that hour. And as I said, people further north will be able to see a a total annular eclipse, which basically means there's a bright ring around the outside. But
Yeah.
anyway, as I said, for those who are living in more northerly areas, watch the rising sun on Thursday,
But not with the unaided eye.
but not with the unaided eye. Yes, thank you.
Oh, okay.
It's really bright.
Yeah, there's lots of,
Will be covered from Chicago. I mean, like 50%, something like that, when it's rising.
I'm not actually sure. I actually don't know the latitude of Chicago, so I can't help you with that.
we can probably find, those of you who are interested can probably find plentiful information online about what it'll look like from where you are. Thank you, Abby. There's also another great eclipse coming up in a couple of years. You know, we had one in 2017, I think. We've got another one coming up, I think, in 2023.
There's 2024, isn't it? Isn't there a big one then, John?
Oh, I
Well,
remember it's a
well,
couple
yeah,
years out, but I don't remember which year now.
I'm already conspiring.
It's not as dry.
It happens during the school year, and I'm already conspiring with fellow faculty members to try and find a way to make it into an assignment.
Nice,
Yes. Mhm.
nice.
I like that.
All right, so talking about theorists and neutron stars, you know, that
Do
kind
we-
of gets into the
do we have a
calculations.
theorist available?
We happen to have a handy
Just-
theorist
just
here.
happened to. Oh.
And speaking of neutron